right, we're right on time to start the next talk by Mike Mandel. Mike Mandel, I'm using a script because he already has a very long history. So Mike got his PhD from Columbia in 2010. He spent a couple years at the University of Montreal as a postdoc, then went to work as an algorithm developer at Audience for a couple of years, then on the road again to Ohio State for 3 years, and he just joined in September CD University New York, Brooklyn College. He's going to talk today about his great experience. It's great. It was great, right? At the Jelinek Workshop this summer in Seattle, and in particular about his work on multi-channel spatial clustering for far-field speech recognition in mismatched conditions. I made it. All right, Mike.
Okay. Yeah, I wanted to change my the title of my talk a little bit from the brochure, so it's a little long. Multi-channel spatial clustering for far-field speech recognition in mismatched conditions at the 2015 Jelinek Workshop on Speech and Language Technologies. So I'll actually go in the opposite order in the talk, but let me just tell you a little bit about what the Jelinek Workshop is, tell you about our team on the workshop, the far-field speech recognition and mismatched conditions team, and then about the work that I primarily focused on over the summer, multi-channel spatial clustering. So to give you an overview, the Jelinek Workshop on Speech and Language Technologies is an intensive 6-week summer workshop. It's kind of a research hackathon. The idea is to get together a few international teams of leading professionals, grad students, and undergrads, and bring together diverse perspectives on important problems in speech and language technology. It's preceded by a 2-week summer school for the students in all the project areas, so they get up to speed and everything. It was previously known as the Johns Hopkins CLSP Summer Workshop Series, so you may know it by that name. There are actually a number of people here who participated, so I should say off the bat that any errors or omissions are my own fault. So the goal of the workshop is to advance the state of speech and language science. Sort of secondary goals are attract students to the field, prepare them for research, get them working on exciting problems with smart people, and get them psyched about it. And also to create research infrastructure, have an impact on the field, and establish lasting collaborations. So you may have heard of some of these previous projects that grew out of the workshop. So the open source ASR framework Kaldi was from the workshop. The machine translation toolkit Moses, using I-vectors for speaker identification, weighted finite state transducers in ASR, dynamic Bayesian networks for ASR. Now, a lot of these ideas had been percolating before, but sort of got a big boost by having this focused effort over the summer at one of these workshops. So in 2015, this was the 20th meeting. It's the second as the Jelinek Memorial Workshop. It was held at the University of Washington, and this is the first time it was mainly funded by industry. So the price tag was pretty high, at least from my perspective. But there were a bunch of great sponsors: Microsoft, Google, Amazon, Mitsubishi Electric, NSF, DARPA. And if you add up, 50 people working over 6 weeks, that's 7 sort of person years of effort on 4 different projects. Let me tell you about those projects. The first one was continuous wideband machine translation. This was a team led by Chris Dyer from Carnegie Mellon. And so continuous in this sense means continuous space representations of words, so vector space representations of words, deep learning. And wideband means utilizing context from the word level, from the sentence level, from discourse level. So trying to combine all of these different levels of context to do better machine translation. The second team was called Probabilistic Transcription of Languages with No Native-Language Transcribers. And the team leaders were Mark Hasegawa-Johnson and Adrian Casey Lee. There were sort of 2 efforts in this that they pursued. One was the acoustic approach, and the other was the electric approach. So the acoustic approach was if you have some speech in a language that there aren't a lot of transcribers around, can you train a speech recognizer to recognize it? Can you do anything? And their approach is to have non-native speakers listen to it and just transcribe phonetically. And if you can translate their phonetic transcriptions into appropriate characters and put several transcriptions together, you can get some kind of signal that you can train a recognizer with, and they were fairly successful at that. The electric approach was to use EEG for the same non-native speakers to try to just read their minds and predict the speech that they had just heard. The third team was structured computational network architectures for robust ASR. This was led by Dong Yu, and it was inspired by their recent release from Microsoft Research of the computational network toolkit, which lets you build sort of arbitrary computational graphs and do stochastic gradient descent on it on a lot of data. And so to test that out, they built this very complicated network to do prediction, adaptation, and classification for ASR, and trained it using this toolkit. And finally, this is our team, the far-field speech recognition and mismatched conditions team, led by John Hershey, who you heard from earlier. So these are all the people who were on the team. There were senior members who were there for the whole time. There were senior affiliates who were in Seattle for part of the time, grad students, undergrads, everyone. It was a great team. Let me tell you about what we worked on a little bit. So the goal of this far-field speech enhancement task is to generalize across mismatched conditions. We typically find that speech recognizers work quite well when you test on the conditions that you train on. But if you try to generalize to a new situation without any training data, then usually things fail. So new conditions can be microphone array geometry. It could be reverberation. It could be noise types. It could be the number of sources. And so we pursued a number of approaches. The sort of umbrella was deep neural networks infused with generative modeling, used for active learning, and built with flexible input-output encodings. So here we put together some benchmark systems, and this is kind of the canonical task that we did a lot of testing on. If you have this recording.
Excluding autos, sales increased 0.3%.
So that's from Chime 3 corpus, which is real recordings of tablet usage in noisy environments. You can train a match system to get 9% word error rate on that. But in mismatched conditions, so if you train your recognizer on meeting recordings from the AMI corpus, the best we could do was 33.4% as a baseline, sort of throwing in all the bells and whistles. So can we bring those numbers closer? I mean, that's sort of the problem that we're trying to solve, is that when we've got the right data, we can do pretty well, but when we don't, we're kind of out of luck. And the real thing is that, let's see, I'll talk about that a little later, but imagine that you're thrown into a new situation. You have no idea what the microphone array geometry is or the noise characteristics of the room. How can you recognize speech in that situation? So we pursued a few different approaches. There were some single-channel methods, some multi-channel methods. In terms of single-channel, time delay neural networks for acoustic modeling. That was an approach where it's sort of a convolutional network, but you can drop some of the computations to be more efficient. Also, latent similarity networks, which is this middle picture here, where you're learning from parallel data to try to get the hidden representations of the noisy speech to be similar to the hidden representations of clean speech for the same utterance. And then data augmentation using noise adaptation vector. So you train a clean acoustic model here, and then you keep that fixed and try to learn another model here that can take noisy data and use that to modify the hidden representation of the clean model such that it does okay on the task, and then you can use that representation as kind of an unsupervised index of the noise conditions. So in terms of multi-microphone approaches, there was one successful approach using DNN-based beamforming, so using a DNN to predict beamforming filters, and that worked pretty well. Also iterative single channel enhancement and beamforming, so sort of putting together some LSTM single channel enhancement with beamforming. We tried some more sort of radical approaches, deep unfolding of Hagai Tyus's 2003 model, and deep clustering, as you heard earlier. And then what I'll tell you about, which is multi-channel spatial clustering. So that was kind of a whirlwind tour of the workshop. Let me tell you about some more technical content here. So I'll tell you about, sort of give you an overview, talk about binaural spatial clustering, how we can generalize that to multi-channel, Messel-driven beamforming, and then show you some experimental results. Okay, so imagine that someone hands you a multi-channel recording. You need to recognize it. Perhaps you have a video hosting website that gets multi-channel uploads. Perhaps you have an operating system for mobile devices that could have different microphones and different configurations, hypothetically. So can we take a recording like that and do something reasonable with it, use spatial information from these microphones without having to calibrate and do all sorts of work on it ahead of time? So the argument that I'm going to make here is that discriminative training tends to overfit on the training conditions. And so especially if you don't know the proportion of conditions or the types of conditions you're going to see at test time, that can be a problem. And so one way to address that is to use generative models just for the highly variable characteristics. So can we do generative things for characteristics that we know less about, but still use discriminative things for the ones that we know more about? So for example, for speech, we kind of have a good idea of the amount of variability that we're going to see in speech and in speakers and maybe even in noise. But I will argue that for spatial scenes and for microarray geometry, it's more variable. Like it's sort of less known what kind of array you're going to see, or what kind of, where the sources are going to be in space relative to the array and relative to each other. So maybe we should use generative models for those parts, but then still use discriminative models for everything else. So that leads to the idea of spatial clustering. And so we can generalize to mismatched conditions in these respects using unsupervised clustering. So the basic idea is to group spectrogram points based on their direction of arrival, so that you can use spatial information, the where, but remain agnostic to the content of each source, the what. Now, of course, you can incorporate content information later, but at the moment, we're just going to use spatial information. So I think it's illustrative to talk about how to do this with 2 microphones first. That's how the project started, so I think it's a good way to get into it. So humans localize sound using a couple of cues. One is the inaural time difference from the path length between 2 ears. And that leads to, at different frequencies, different phase differences between channels. So if we take a spectrogram of the right ear and a spectrogram of the left ear, like this, you can see a phase difference here, which is this kind of rainbow color. Because of this delay, the sound gets to the right ear before it gets to the left ear. And then similarly, the head creates a shadow for high frequencies, so the head blocks out high frequencies at the far ear. So that leads to an inaural level difference from the head shadowing. So you can see that here. So equal levels of the 2 ears is sort of this yellow or orange color. And so this blue indicates that there's a lot more energy at the right ear than the left ear at certain parts of the spectrogram. I can play this for you.
Tim takes Sheila to see movies twice.
So that's for a source that's off to the right. For a source that's straight ahead of you, the 2 ear signals are much more similar. You can see that for the level difference, they're mostly around 0, although where the speaker is more active, it's closer to 0, and then where it gets the speaker's less active, there's less speech energy, it's a little more random, so there's sort of higher variance but similar mean. And similarly for the IPD, it's pretty close to 0 where the speech is active, but then elsewhere it's kind of random. So this is the other mixture.
Presently, his water brother said
So if we put those together, we get this.
Take Sheila to see movies twice.
And so you can see that in the ILD and in the IPD space, you can see both of those signals. So you can see the rainbow here, and you can see the blue. And so when the speaker that's off to the side is active or is louder, it's their cues dominate. So the rainbow dominates the spectrogram in those regions, and where the speaker that's straight ahead dominates, the light blue regions show up. And so you could imagine using these features and these features as well to segment and cluster spectrogram points. So we need to be able to figure out which spectrogram points come from the blue regions, which ones come from the rainbow, and then our problem will be solved. Now this is easy to do if you have the sounds separate to begin with. You could just analyze them like I did for those first couple examples, and you get different parameters. So this is the time difference for there's a blue source and there's a red source. This is the level difference between the two ears as a function of frequency. This is time difference here and probability. And this is the phase difference that's predicted by these across frequency for the two sources, source 1, source 2. So if we have a mixture, how can we hope to get these two estimates? And the key insight, I guess, is that if you have the masks already, you can get a pretty good estimate of the parameters of the sources, the spatial parameters of the sources. And similarly, if you have the spatial parameters of the sources, you can do a pretty good job of figuring out the masks. And so we can use this EM-type algorithm. We can iterate back and forth between these two approaches or these two stages and do a better job of both. So we can refine both the masks and the parameters. So this is what I call model-based EM, source separation and localization. So we have a set of parametric source models for level difference and for phase difference. And in general, you can use any model that can compute probabilities for individual time frequency points. So for a point in the spectrogram, you can say, what's the probability that this point came from this source or that source, so that we can compute the masks. And then we need to be able to estimate the parameters from those individual time frequency points. So we know that this point came from source 1, so let's update source 1's parameters a little bit to be more like that observation. So we can use EM to estimate the parameters and the global masks. So I'm not going to get too much into the details, but the model is basically, we have a Gaussian model for IPD for the phase difference. So this is a Gaussian across frequency, so it's sort of a 500-dimensional Gaussian diagonal covariance with, this is showing the probability across IPD here. The ILD we're also modeling as a 500-dimensional Gaussian diagonal covariance. And then the time difference shows up as a discrete latent variable. So we're looking at sort of over a set of different time differences, does one of them fit our observed time difference better? And that resolves issues with spatial aliasing and ambiguity if your microphones get too far apart. And so this is basically a big Gaussian mixture model. And so there's one Gaussian per source and per delay. And so we can use EM on this pretty easily and find the masks and the parameters. So the E step, we have the parameters of these Gaussians. We compute the posterior probability of each point under each Gaussian, and that gives us the masks. And then in the M step, we have the masks, and so we compute the weighted sufficient statistics of the observations, and we can update the parameters. So for example, for this mixture that I've been showing you, this is the ideal mask. So if you know the two separated sources ahead of time, you can get a mask that looks like this. And Messel gives you a mask that looks like this. And it sounds pretty good.
Presently, his water brother separates.
So, okay, that's for 2 microphones. Can we scale that up to multiple microphones? The trick is that if you want to scale it up to multiple microphones, we need some way to sort of make these taus, these delays, talk to each other. We don't want to have an exponential number of delays or an exponential grid of delays that we're testing. So how can we do this efficiently? So there's a couple ways. The first is if you have calibration information. then you can use calibrated multi-channel MESL. And so in this way, you can compute the phase difference and level difference between pairs of microphones, but then translate those into through a geometric mapping into a global coordinate system. And so you can do that. You can you can get sort of one set of masks, one set of parameters, and do this EM approach. This is something that John Barker explored at the workshop, but is still, we don't have a lot of results for it yet. The other way that I'll be talking more about now is to use uncalibrated multi-channel MESL. So here we're still modeling the phase and level difference between pairs of microphones, so all pairs of microphones. And then each pair has its own binaural model, which is kind of silly, but it lets us do this generalization so that we don't need to know anything about the array geometry. And the way that the models are coordinated with each other, the way that the pairs are coordinated with each other, is through global masks. So you compute masks locally for each of the sources, and then and then all of the different pairs send their mask for source 1 to the same place, and they get combined for source 2, for source 3. And so you can think of it as instead of having to know how to translate geometry from one pair of microphones to another pair of microphones, we're going to just say the masks should be the same. So the regions of the spectrogram dominated by source 1 should be the same whether you're in mic pair 1, mic pair 1, 2, or mic pair 1, 3, or mic pair 2, 3. And so by coordinating them through these masks, we can avoid having to do any sort of calibration of the array or know anything about the geometry. And so we can generalize automatically to new geometries. OK, so say that we've done this. We have some masks. Now we want to do some beamforming. With the 2-channel signal, you could just apply the mask, say, to one of the channels and call it the output. But we're using 6 channels here, so that leaves a lot of performance on the table. We could do beamforming to get a much better signal that we could then apply a mask to afterwards. So the way that we're going to do that is minimum variance distortionless response beamforming, MVDR beamforming, which minimizes the noise energy while preserving signals from a look direction. So this is sort of our simple signal model, so that we have a one-dimensional source. This is in time or per frequency. And so that's coming from a particular direction. So this D is a plane wave direction. And then we add a multi-channel noise to it and get our observation. So the MBDR beamformer tries to find a W. So we're going to use W here, so that W Hermitian transpose Y is minimum with respect to W. But still, we preserve speech from this look direction, so that the beamformer times the look direction is unity. So we have unity gain at the look direction, but try to minimize all the energy everywhere else, basically. So this basically means we need 2 parameters for this. We need some way of specifying the look direction, and we need some way of specifying the noise covariance. So this is the noise covariance across space, and how the energy or how a signal at one microphone relates to a signal at another microphone. And so we can get both of those from MESL. And so this is kind of the diagram. So we have multi-channel noisy audio. It comes into MESL. MESL does its clustering and gives us a mask out. It also gives us the directions of the sources. So the beamforming needs a direction. It needs a noise estimate. It needs the multi-channel audio. And then we can also apply a post filter if we want at the end, so that when we have just a single channel of audio coming out, we can apply a mask to it and attenuate regions that are dominated by noise in a nonlinear way to get an extra little boost of performance. And so for the experiments, we compared a few different ways of doing each of these 3 things. So for the look direction, there's this paper by Marasudin for using an estimate of the noise covariance with an estimate of the mixture spatial covariance. So in this way, you don't need an actual look direction. You can compute it from the mixture. So that was our baseline that we compared it to. And from MESL, you can create this sort of steering matrix by looking at all of these pairwise phase differences. and so you can use that as the steering vector from Messel. For the noise estimate, the baseline is just looking at the 800 milliseconds of speech before the talker started, or sorry, the 800 milliseconds of signal before the talker started speaking. And so that gives you some estimate of just the noise, but the problem is that if the noise is changing over time, that might not keep up, might not be current. And so the alternative is to use Messel and to say that when the mask that says it's speech is 0, then we're going to estimate the noise covariance, the noise statistics from there. But when the mask says it's 1 and it is speech, we won't compute statistics for that. And then for the post filter, we compared baseline of not using a post filter to a baseline of using the Messel mask as a post filter. And so for the post filter, essentially, if you think of a spectrogram and a mask as kind of a cookie cutter, the cookie cutter will cut out the noise on the spectrogram. It'll attenuate time frequency points that are dominated by noise and preserve the ones that are dominated by speech. So how did we do? I guess just to give you a few details about the setup. First, we trained on this AMI multi-mic recordings. So it's an 8-mic circular array, 10 centimeters. It's far field, it's reverberant. It's from meetings, so there's not a lot of people talking over each other. There's not a lot of background noise. There's some air conditioners and things. Not a lot of non-stationary noise. We used state-of-the-art DNN, acoustic model, speaker adapted, discriminative training. And we tested on the Chime 3 real recordings. So these were, it's a sort of a tablet scenario like this. So it's a little bit closer than the meeting recordings. But it's very noisy. So the SNRs are 0 or maybe a little bit below 0 dB or a little below. So different geometry, different number of microphones, but that's fine. So here's the results. So using just beamformat alone on the Chime 3 data gave well, let's see, so a test set error of 36.2%. If we use beamformat with the Messel mask, we can get that down to 31%. If we use the best Messel MVDR system, we can get the development set error down below that, but the test set error is still a little higher. There's a few tweaks for that, but the best system that we had here is using this the Sudan's look direction, but with the Messel mask for the noise estimate and the Messel mask for the post filter. So we had, if we use a slightly different initialization for Messel, we can get the test set error down lower. It's not quite a fair comparison, but the dev performance and test performance were quite different on this data set, which makes it a little bit hard to, I mean, this is the problem that we're trying to solve, is that we have mismatched conditions between the dev and the test set, and so it's a little bit hard to know if we've picked the right system to do this. But we're achieving performance at least as good as using this this beamformer plus our mask for word error rate, and we're doing it in this totally unsupervised way, and using a more sophisticated beamformer than beamformer can. Let's see what else. So I'll show you some examples. This is the original sound.
Excluding autos, sales increased 0.3%.
This is with beamformat with no post filter.
Excluding autos, sales increased 0.3%.
So you can definitely hear the noise is reduced a lot. There's still a lot of low frequency noise because the delay in some beamformer has trouble for the low frequencies. This is with Messel MVDR without a post filter.
Excluding autos, sales increased 0.3%.
The overall gain is a little bit louder, but it does a much better job at these lower frequencies. You can definitely resolve that information much better. And this is using the Messel MVDR beamformer with the Messel mask afterwards. So we're doing some nonlinear, doing 9 dB of nonlinear suppression afterwards, and it looks much better. You go from that to that.
Excluding autos, sales increased 0.3%.
There's still very lowest frequency sound there, but it's much better. This is using pure MESL MVDR, so without the Sudin approach, but with our IPD estimates. And you can actually see that it looks much cleaner in the high frequencies. There's not this sort of frequency-dependent suppression that we're seeing here. But at the very lowest frequencies, around 500 hertz, there's a little bit more noise leaking through here. So this is why this approach does a little bit worse for the ASR. So this was getting 36.1 versus 32.6, but I think with a little bit of tweaking, we could improve that. Play that for you.
Excluding autos, sales increased 0.3%.
And this is what happens if you really crank up the nonlinearity. So we'll listen to it.
Excluding autos, sales increased 0.3%.
So there's much less noise, but there's a lot of artifacts. And so it turns out that just using 9 dB of suppression works kind of the best because of this. So if you go too far, then you end up distracting the recognizer with artifacts, versus if you sort of hold back a little bit, then these artifacts are lost in the existing noise, in the ambient noise. So really, I think the way forward for this is to so this is just using spatial information. So if we added in a model of speech with this, I mean, it's clear that this musical noise is not speech. It's clear that these low frequencies are not speech, but there should be harmonics here. I think that a simple, maybe not simple, but incorporating a speech model into this would be able to take care of these things, and so we could then turn the nonlinearity up a bit. If we had a better, a cleaner mask here, we could turn the nonlinearity up and hopefully turn the noise down. This is the close mic signal.
Excluding autos, sales increased 0.3%.
So you can hear even, it's difficult to train, say, a DNN to denoise this because there's several kinds of artifacts in this. There's breath noise, there's clothing rustling and touching the microphone, things like that. So this needs to be cleaned up a little bit. So because these recordings were made live, people were actually using the tablets, the best reference that we have is a lapel mic, or I guess it was a head-mounted mic. So they have these for the training set. Can we take advantage of these? That would be something else that would be useful to do. So let me summarize by saying, so MESL is a Gaussian mixture model of interaural level and phase differences. It's unsupervised clustering of time frequency points into several sources. It's able to generalize to multiple channels by modeling pairs of microphones, and we can use it to drive beamforming using various outputs from it. We can reduce the word error rates by 10 to 17% relative, and the code's available from my GitHub page if you want to try it out. Thank you for your attention.
Thank you. Questions? Elliot?
Hi, thank you. I actually have a pretty specific question. Just curious, how much do level differences help when you're working with an array of microphones where you don't have like occlusion due to the shape of the head?
Not very much, but actually for chime 3, there was one of the microphones was rear-facing, and so that had some pretty significant level differences.
Okay.
The other microphones didn't have much level difference between them. So you can include that or not, and it helps for chime 3, but for just say a freestanding array, it wouldn't make much difference.
Okay, thanks.
So you use the back microphone in these experiments?
Yeah.
Did you have a detector for the utterances where it wasn't helpful?
I just used the default detector that, if there was a signal, if there was a wire loose or something, then, so the nice thing about this is that you can, if there's only 5 good channels, you can use 5 good channels. If there's 6 good channels, you can use all of them.
So you use the baseline detector?
Yeah.
Okay. I heard it like the having a good detector on that mic helped a lot.
Did it? Okay.
Rumors, though.
Okay.
Another question? I have another question. All these results are with retraining?
No, there was no retraining. This is just the baseline recognizer trained on AMI. I threw these recordings at it, and it did what it did.
Is it possible to retrain, or is it in this framework that wouldn't really make sense?
I mean, I guess it would make sense. I mean, you would probably lose some of the generalization, but I mean, you could at least sort of learn to deal with the sorts of artifacts that you get from this.
It's different data, so it's hard to.
It's hard
different microphones, so I guess it would be. Even the retraining may not buy you so much.
Yeah, but it would be worth trying.
Okay. Thanks. Have a question? Arun?
So did you get any gains in matched conditions? I understand this was mainly for mismatched, but did you ever evaluate on the Chime 3 test set?
Yeah, so for Chime 3, I think this gave, it was around 10% relative improvement, maybe a little bit more. So from 18% word error rate to 16 or so, something like that.
Questions, comments? Yeah, Dan?
Hey, well, I may as well ask them, what are your thoughts about moving sources within this model?
That's a good question. So this version is assuming sort of a batch, so stationary sources. Some work from Sharon Ganat's lab has used sort of a recursive EM approximation so that you can have the parameters change over time. And they found that it worked pretty well for moving sources. So I think it's doable.
Okay. Well, if no more questions, let's thank Mike.
These are the placements. Oh. And our T-shirt. Okay.
Is the call for workshop still open for
I think it closed last week, so
too bad.
Yeah, the timing was.
So next year, if you want to organize a Jelinek Workshop, stay tuned for the call for proposals from Sanjeev. It's a great experience.